Welcome to this ME1000 video. We are working on modeling the cart for the design project. We're going to put our acceleration equations for the food and the car into Excel and use the explicit finite difference numerical integration technique to determine how far the car will travel. You will be given a spreadsheet like this to use for your DPA-8 modeling, and so what we're going to do here is just walk through the spreadsheet, talk about what you'll be given and what you'll need to do, how you'll use the spreadsheet to do the modeling that you need to for the DPA. Let's start by looking at the design parameters that are here in the gray box on the left. The design parameters given include the radii, the masses, the gear ratio, the coefficient of rolling resistance, everything that we know about the problem, starting with the maximum potential energy, which is the 2 spam can meters. If you do the math, that is around 6.66 joules. When you get this spreadsheet, these values will not be here, and so you'll need to populate them with things that you've measured or things that you know about your own device. Now let's take a look at the columns over here on the right. We first of all have a column with the step number and then the time, which we can populate by multiplying the step number times the time step, which is dt_1. So I can go ahead and populate the entire time column. You'll notice if I change the value of the time step, then my times will all change, and that's exactly what I want to happen. Okay. We've got two sections. The first, we've got 3 columns: acceleration, velocity, and position for the spam or the food item. And then I have 3 columns, again, acceleration, velocity, and position for the car. You will be given the equations and initial values here in the first couple of rows of the EFD section of the worksheet. So let's take a look and see what's here. In the AF column is the equation that we derived in class for the acceleration of the food item, and we can go ahead and carry that all the way down. That is a constant acceleration until, of course, the food hits the bottom. For the velocity, the initial velocity of the food item is 0, and we are going to use 0 for the initial position of the food item as well. So it's going to start at a position of 0. Down is negative according to our convention, and so it's going to go from 0 to minus h. And that will be important to keep in mind. Okay, now let's take a look at the section of the worksheet that corresponds to the car. So we've got acceleration of the car, velocity of the car, and position of the car. For the acceleration of the car, we've entered an equation that refers to a sub f in column H, so that's quite simple. Basically, we multiply the radius ratio times the gear ratio with a minus sign times a sub f to get a sub c. The initial velocity of the car is 0, and the initial x position of the car is 0, and so that takes care of our initial values. The next thing is the EFD equations themselves. So you'll see for x sub c, we have an equation that takes the previous position from m3 and adds to that the previous velocity times the time step. For velocity, we do the same. We take the previous velocity from L3 and add to it the previous acceleration from K3 times the time step. And of course, we've done the same thing over here for the EFD equations. And so we can go ahead for now and carry these all the way down as far as we have time steps. You'll recall that the equation we derive for AC, which is this equation here that refers back to AF, is acceleration of the car during the propulsion phase. And so we need to switch that to the acceleration of the car in the coasting phase at the right time. And that time, the right time, is when the food item hits the bottom. The food item is going to hit the bottom when this position value gets to minus h, or h in this example is 2 meters. So if we scroll down here until we get to minus 2 meters, right here, in between here, is where we're going to end the propulsion phase and enter the coasting phase. And what we need to do is change at that point the acceleration of the car to simply be the force of rolling resistance divided by the mass. And so we need to put an if statement here in the AC column to accomplish that. So let's go ahead and do that. So equals if, we're going to look at the position of the food, so that would be J3. So, and because of the fact that we're starting at 0 and going negative, it's going to be best to put in an absolute value here. So if the absolute value of J3 is greater than H, again 2 meters in our case, then we want to use just the rolling resistance force divided by the total mass. So FRR divided by M tote. And otherwise, before we reach that condition, we want to use the equation that was there already, which was the acceleration in the propulsion phase. So let's see what happens. So we haven't reached 2 meters, so we're still getting that same value, so that's good. Let's carry that down and see if we switch over to a different acceleration. And in fact, we do right when the position of the food gets to -2 meters. Okay, great. So we have managed to incorporate both the propulsion phase acceleration and the coasting phase acceleration of the car into our spreadsheet. So let's take another look at what's happening here when the position of the food reaches -2 meters. So in other words, it's bottomed out. You can see that our acceleration is switching from the propulsion value to the coasting value, although you might wonder if this is actually right. In the coasting phase, actually the force is going to be a resistive force, so it should be negative. So when we put our if statement in, did not include that negative sign, so let's go and fix that. So if the absolute value of the food position is greater than our H value, then we're going to have a minus FRR divided by M total for the acceleration, and that other equation was fine, so let's go ahead and fix that and scroll down and see if we now have a negative acceleration. Okay, good. That's better. So looking here again at that transition, we can see that in the propulsion phase, the car is going to go 5.4 or 5.5 meters, somewhere in there. I am using a fairly large time step just so I don't have to scroll so much in this demonstration, but when you do your modeling, you will want to use a smaller time step so that you get more accurate values. Okay, so 5.5 meters in the propulsion phase, the car is going to travel more distance in the coasting phase, and to determine how far it will go total, we need to scroll down until we see the velocity of the car go to 0. So scroll down and down and down and down. Velocity is getting smaller because our acceleration is negative, and we're getting closer. So right here, the velocity of the car passes through 0, and so the total distance traveled, propulsion plus coasting, for the values that we've input here is around 29 meters. As you start varying your design parameters to see what effect that will have, you're probably going to get tired of scrolling down to find the time at which velocity goes to 0. So here we go, scrolling down to find that again. And so one thing that'll be really helpful is if you put an if statement into the position column, so that when the velocity goes negative, you'll just end up with a 0 in the position column. And I'll show you in a second why that will be useful. So let's go back up here and add an if statement. So if the velocity from the column to the left is less than 0, so if it's negative, we'll just say that the position is 0, and otherwise we'll use the equation that we had. Alright, so let's carry that down and now scroll down and take a look. see if that worked. Okay, so here our velocity went negative, and our position went to 0. Of course, that's not realistic. Our car is not going to jump back to 0. But what this lets us do is find the final position, the total distance traveled, by looking for the maximum of this column. And so if we go back up to the top, over here we can say maximum distance, and that'll be equal to the max of this column. So there's our 29 meters. Let's put some units there. And now if we change a parameter, let's say we just redid our measurements for rolling resistance and our coefficient is actually 0.03 instead of 0.01, it's quite easy to see that now the maximum distance is going to be reduced to 9.8 meters, and we don't have to go searching for that. So that will be helpful for you. And with that, I think you're ready to go to do the modeling for DP8. So have fun. Thanks.